In this lecture, we're going to revisit functions. Oops. So just to refresh our memories, a function is a relation between a domain A and a codomain B, and it has these properties. For every element in A, there is an element in Y that is part of that relation. And for all elements in A, and for elements Y and Z and B, if the ordered pair XY is an element of the function and the ordered pair XZ is an element of the function, then Y equals Z. So in other words, an element in X, or X, an element in A maps to just one value in F, not multiple values. Now, some other terminology is also used for the idea of a function. F of x is also known as the image of x under F. And we have the idea of the range, and the range is the set of values that we map into on our codomain from our domain. So there's also this idea of an inverse image of x, and that's where we go from the codomain back to the domain. So in the function, we start with the codomain and see what it maps into in the domain. Arrow diagrams help us explain these concepts a little more clearly. So here we've got two sets, X and Y, and we have a domain of X1, X2, X3, X4, and a codomain of Y1 through Y5. And a function maps the values of x. Every value in x must be mapped to a value in y, and every value in x must be mapped to only one value in y. So here we have our function, and it's denoted with arrows in this arrow diagram. And we have our range of y1, y3, and y4. These are the values in y that actually are part of the function. And of course, all the elements in x are part of the function. So the arrow diagram above, right here, does define a function. Again, every element of x has an arrow coming out of it, and no element of x has two arrows coming out of it. So let's consider this function where we have x with is a set with the elements a, b, c, and y is the set with the values 1, 2, 3, 4. And we have the function defined by this arrow diagram. Again, note that every element in x is mapped to a value in y, and every element in x is mapped to only one value in y. So that does make it a function. So let's look at the domain and codomain of f. Find f of a, f of b, f of c, and what is the range, and so on. So the domain of f is just those values that are in x, a, b, c. And then the codomain of f is those values in the set y, 1, 2, 3, 4. So that's our range and our domain and codomain. And then f of a is going to be 2, f of b is going to be 4, f of c is going to be 2. Like we see here, the range of f is 2 and 4. So those are the actual values in y that are participating in the function, 2 and 4. Then is C an inverse image of 2? So C is, yes, it is an inverse image of 2. And is B an inverse image of 3? Well, no, because C is an inverse image of 2 because if we start at 2, the inverse of the function takes 2 to C. The function takes C to 2. The inverse takes 2 to C. So there's no inverse relationship from 3 to B. 4 is the inverse of B. The function takes B to 4. The inverse takes 4 to B. And then what are the inverse images of 2, 4, and 1? So inverse images of 2 is A and C, and 4 is B. So looking at that, inverse image of 2, we're going to go to A and to C. Inverse image of 4 goes to B. And then as a set of ordered pairs, the function as a set of ordered pairs is here, A2, B4, C2. Of course, the inverse image of 1 is null because there is no relationship between 1 and any of the elements in X. So we have A2, B4, and C2 as our ordered pairs in the function. Oops. Okay, so each element of the domain must have an arrow coming out from it, but there can be elements in the codomain to which no arrows point, just in the definition of a function. So when we're going to test two different functions for equality, this is what that means. If we have the function that maps f to y, if we have the function f that maps x to y, and the function g that maps x to y, then f equals g if and only if f of x equals g of x for all the elements in the domain X. So let's take a look at these. We have a set J3, 0, 1, 2, and we have these functions of J3 to J3. So for all x in J3, f of x is equal to x squared plus x plus 1 modulo 3, and g of x is equals to x plus 2 squared modulo 3. So the question is, does f equals g? Well, let's look at that. So what we're going to do, here's our domain. X has the elements 0, 1, 2. We're just going to find out what the values of f and g are and see if they're equal everywhere. So just plugging in 0, we get 0 squared plus 0 plus 1, 1 squared plus 1 plus 1. So we get 137. Then we're going to do the modulo. So 1 modulo 3 is 1, 3 modulo 3 is 0, and 7 modulo 3 is 1. Now, so that's the entire range for f. Let's look at g. So x plus 2 squared is 4, 3, 0 plus 2 squared is 4, 1 plus 2 squared is 9, and so on, and we get 4, 9, and 16 as our values, intermediate values in G, and then we do the modulo 3 on those values, and we get 4 modulo 3 is 1, 3 modulo 3 is 0, and 16 modulo 3 is 5. So the range is 1, 0, 1. So we have range 1, 0, 1 and range 1, 0, 1. So in fact, they are equal. Okay, and just the f plus g is equal to g plus f, and this is a short proof of that. Okay, let's look at some examples of functions. There's an identity function that takes a function to itself. So whatever you start with, that's what you get in your identity function. So when we multiply the identity function times, say, a raised to the k, a sub ij raised to the k, or theta of z, the identity function for that one, what we end up with is the same values. In other words, the same functions. So, the identity function does not change the function that we're dealing with. So it comes out just the same in both cases. And logs are another example of a function. And a logarithm of base b of a particular number is the number that you raise, the exponent you raise b to in order to get the value x. So log b of x is going to be that exponent we see here, b raised to the y equals x. And so you have different bases, base 2, base 10, and so on. So let's look at a couple of these. The log 3, log in base 3 of 9, log in base 2 of 1/2, and log in 10, log in base 10 of 1. So log of 3, log of base 3 of 9 is 2 because 3 squared, in other words, our base, the exponent 2, 3 squared is 9. And then similarly here in base 2, 1/2 is equal to -1 because 2 to the -1 is equal to 1/2. And then in base 10, 1 is equal to 0 because 10 raised to the 0 is equal to 1. And then d, log of base 2 of a number 2 raised to the m is equal to m, because just by definition, m is going to be the exponent to which 2 must be raised to obtain 2m. And then 2 to the raised to the log base 2 of m is equal to 2, because log 2 of m is the exponent to which 2 must be raised to get to m. So we have another idea of a string as a finite sequence of elements. And the number of characters of a string is called the length of the string. And we have sometimes a null string, which is a string without any characters. And in that case, it's usually denoted to have a length of 0. Now, one of the things we do with strings is we can encode them, and we can also take a string of zeros and ones. So we have a finite sequence of zeros and ones, and whenever they're communicated across a transmission channel, they're often encoded. And that way, you have some error encoding so that if an error happens, one of the bits is flipped by accident, you can restore the original message. And so just as a simple example of this, you would take a string of zeros and ones, and you would just triple each one of the elements in it. And then you would have an encoded message 3 times the length, but if one bit flipped, you could just use the other two in the triple to determine what the correct value was. And then you can decode that string by just reversing the function that you applied. So if we tripled the number of each element in the string, here we would just get triplets and determine which one, what that maps to. So 3 ones would map to a 1, 3 zeros would map to a 0. If we had 2 ones and a 0, that meant probably one of them flipped, and so we would go with the 1 because there's 2 ones and a 0. So that's encoding, is when we place a code on a string, and decoding is we take the encoded string and we convert it back to the original string. So they have this E of S is a string that's obtained from the original string S by replacing it with the encoded values. In the example she gave in the book, it's you write the bit 3 times. And then you have a decoding function that takes the string T, which has been transmitted over the line, and you're going to replace the consecutive triples of a single copy of what's in those triples. So there's some amount of error correction that can be done when you're transmitting over noisy communication channels, and that's the value of that stream of bits. And okay, let's talk about Boolean functions. So we used input-output tables and truth tables for digital logic circuits. The input-output table defines a function in that the elements in the input columns can be regarded as ordered tuples of zeros and ones. And for that combination of, zeros and ones, you'll have a corresponding 0 or 1 as the output of it. And you could replace zeros and ones with T's and F's, but let's go forward with the zeros and ones like we considered in digital logic circuits. So we have an n place, and n is how many of these columns we have in our Boolean table, where we are putting in, okay, we've got, for our variables, we have X, Y, Z, and we've got to get all the combinations. So X, Y, and Z can each take on 0 or 1. What are the combinations? Well, 2 to the third or 8. And then we look at each of the combinations of those, and that would be a 3-place Boolean function, and we'd have triples that we're dealing with. But it could be up to n. We could have, as many variables in our Boolean function as a problem dictates. So we're going to stay with a simple 3-place Boolean function, and we want to define all the combinations of zeros and ones, the 3 tuples, for variables x1, x2, and x3. And then the Boolean function is x1 plus x2 plus x3 modulo 2. So we want to describe that using an input-output table. So first thing we have to consider, just how are we going to do one particular combination? So 111 is one of the possible 8 possible combinations. And that would be 1 plus 1 plus 1, or 3 modulo 2. So we get 3 modulo 2, and that's equal to 1. And just as another example, 1, 1, 0 is another possible combination. And that gives us 1 plus 1 plus 0, or 2 modulo 2, or 0. So this is how we will fill in the truth table or input-output table. So like we did with the Boolean functions, we are going to alternate in order to get all the combinations. So we know when you have two possible values and you've got three variables, 2 to the third is 8 combinations. Well, we start with the one variable x3 and we alternate 1, 0, 1, 0, 1, 0, and so on. Next one, we alternate by 2s instead of by 1s. So x2 is 1, 1, 0, 0, 1, 1, 0, 0. And then next one, we alternate by 4s, 1, 1, 1, 0, 0, 0. Then we're going to determine the output, which is just x1 plus x2 plus x3 modulo 2. And we get 1, 0, 0, 1, 0, 1, 1, 0. So this is a Boolean function defined or described with a input-output table. Looks, of course, very much like the truth tables we did in Boolean algebra. So another thing we'll do is check to determine whether a function is well-defined. So we might have something like this, x squared plus y squared equals 1, and it looks like a function, but when we examine it closer, we find that no, it doesn't satisfy either of the criteria. Because for almost all values of x, there's no values in y that satisfy the equation. In other words, what if x was 15? Or what if x was 20? So if x was 20, that would be 400. So 400 plus y squared, what's y squared going to be to equal 1? Over the reals, it's going to be null. There isn't going to be anything. So we don't have the first property of a function is that every value in the domain is mapped to a value in the codomain. And then secondly, we also can have two different values for y that map to a particular value of x. So let's consider if x is 0. So 0 squared is 0. So y could be a 1. 1 squared is 1. Or y squared could be a minus 1. So 0, 1 and 0 minus 1 are both elements in this relation. So that violates the second property of a function. Each value of x is mapped to only one value of y. So it's not well defined because it fails to meet at least one of the requirements, and in this case, it failed both. So let's consider another function. Q is the set of rationals, and you want to map the rationals to the integers. And the way you do that is you just take the numerator. So f of m divided by n is equal to m. So is this function well defined? Well, it's not well defined, and that's because fractions have more than one representation. So we can have the fraction 1/2 equals 3/6. So these are equal in our domain, and yet they're going to map to two different numbers in our codomain. So the two numbers that are equal, 1/2 and 3/6, first one maps to 1, second one maps to 3. So that's a violation of the second requirement of a function. And finally, we can have functions that act on sets. So let's say we have a function and we've got this domain x to y. Y is our codomain. And we have a set A that's a subset of X, and we have a set C that's a subset of Y. Then we have the function of A, and that's going to equal to this set of Y equals f of X for the X in A. And then we have this idea of an inverse image of C, and that's going to be where we have the values in X that map to the C, that are elements in C. So if we look at two sets as examples, we have X, which is our domain 1, 2, 3, 4, and Y, which is our codomain A, B, C, D, E. And we have an arrow diagram mapping X to Y. So we have 1 to B, 2 to A, 3 to D, 4 to B. So if A is the elements 1 and 4, C is the elements A and B. So C is a subset of our codomain, and D is the elements C and E in our codomain. We want to find f of A, f of X, the inverse function of C, and the inverse function of D. So f of A is equal to B. So 1 and 4, 1 and 4, both point to B in the codomain. Hence, the f of A is going to be B. And then f of X is going to be ABD. So X is this entire set, 1, 2, 3, 4, and it goes to A, B, and D, nothing to C and E. Next, we want to find the inverse image of C. So C is going to be equal to 1, 2, 4. So C, we have the values A and B. So A goes to 2 and B goes to 1 and 4. So we have 2, 1, 4 as the inverse image of C. So we start with these elements in C, A, and B, and then what do they map to? Well, 2, 1, and 4. And then the inverse image of D is null, and and that's because D is equal to C and E, and they do not map to anything in our domain. So the inverse image of D is null. Okay. Thank you.